Okay, our next session is going to be about the various test beds, predominantly HOT, the Hurricane Oceans test bed. Jordan Dale, would you like to take over and do your announcing and then your talk?
Sure, thank you, Aaron. And thanks everyone for joining for the last session today. So this session will be focused on the Hurricane and Ocean test bed. We'll start off with a quick overview from myself about the WPO testbeds program. And then we'll get some good updates from Wallace and Jason about what's been going on over in the HOT over the last year. And then following that, we'll have 4 presentations from the PIs funded through WPO's Testbeds program about the work that they've done over the last year or so. So without ado, I'll go ahead and get started with the first presentation. So again, good afternoon. And just to kick off this presentation, this is going to be, again, a quick overview of what WPO's Testbeds program does, with a little bit of a focus on what we're doing with HOT. So for anyone not already familiar with NOAA Testbeds, I just want to reiterate, for anyone not aware, these are collaborative spaces where weather forecasters and researchers can work alongside each other during regular experiments or other types of sessions like hackathons to test and integrate research products into operational weather forecast. WPO's Testbeds program in particular funds projects that align with the operational needs and are suitable for testing and demonstrating new technologies in various testbeds across NOAA. Next slide. Currently, the program is a team of 2. In addition to myself, I really want to highlight Felicia Goriello, who does a lot of the work in the background with coordinating activities across the program. Again, I'll just reiterate that we use our WPO NOFOs to run competitions. Right now, we've been running those on 3-year cycles, and those competitions are how we solicit and fund different awardees. So those tend to be academic partners, but can also be commercial industry and NOAA laboratories. We typically use cooperative agreements for conducting the research, and that basically means that there is more substantial involvement with our NOAA partners in the testbed. And the projects are typically, they all test and demonstrate some new cutting edge type of forecasting technology. Can run the gamut from new models, forecasting techniques, new observational data that's suitable for testing in one of the NOAA testbeds. And the goal is to accelerate the transition from research products into National Weather Service operations through the testbeds. I'll also mention that in addition to funding research projects, our program also funds testbed infrastructure costs, which I will detail later. Next slide. All right, so this slide I probably need to update, but currently and historically, our testbeds program has been supporting 3 NOAA testbeds. Those are the hazardous weather testbed in Norman, the hydrometeorology testbed in College Park, and in particular for this session, the Hurricane and Ocean testbed, which was formerly the Joint Hurricane testbed in Miami. So you can see in the slide here, it's pretty self-evident which each testbed, which Weather Service Center and then OAR labs, each of these testbeds work with. And they're all focused on specific hazard types. I'll mention that with WPO's recent reorganization, the testbeds program will also be supporting the climate testbed starting this year in College Park, and hopefully the fire weather testbed in the next year or 2 located at GSL in Boulder. Next slide. I also want to mention that the testbeds program is not the only WPO program supporting testbeds. So as you saw from some of the sessions and presentations earlier today, JTTI's social science both work with testbeds, and specifically for JTTI, as you gathered in the previous session, they engaged with testbeds through funding some R2O projects and also providing infrastructure support. And historically that has been to HMT, HOT, and HWT. The social science program, which we heard about earlier this morning, supports testbeds through special funding sources like disaster supplementals or BIL. So they have a few projects that are funded through those, which ties back to our session earlier this afternoon about supplementals. And then the S2S program, I don't want to leave out here, but historically S2S has funded R2O projects that work with the climate testbed. Although, as I mentioned earlier, All of those projects will be moving to the Testbeds program this year and going forward. Next slide. All right, I wanted to highlight what the latest research priorities were from our last WPO FY22 NOFO testbed competition for HOT in particular. So these priorities were developed close to 3 years ago now in conjunction with the HOT testbed managers and also the HOT steering committee. So just at a high level, if you want to see more detailed research priorities, you can go look at our old NOFO, but the priorities included improving the operational analysis of the surface wind field and tropical cyclones, developing guidance on best flight track strategies or supplemental observation strategies, improving guidance for TC track and intensity forecasts, improving guidance for TC genesis forecast, applying and integrating relevant SBS methodologies for tropical and ocean hazards, and developing tools or products to help forecasters better interpret conflicting radar and recon data to assess TC intensity and structure in real time. So through this competition we ran in FY22, we ended up selecting 4 HOT projects, and we will get some updates from PIs for each of those projects later in this session. Next slide. All right, so I mentioned earlier on a previous slide that in addition to funding R2O projects, the Testbeds program also supports testbed infrastructure needs, and we do this through sending funds, typically through BOPs on an annual basis. The infrastructure costs are really critical for the testbed operations, and costs for, and not, this isn't for all testbeds, but kind of broadly speaking, fall into kind of 3 different buckets typically. So some of the costs include contractual services. So this might cover testbed coordinators or IT support. Another bucket falls for equipment needs. So that can be hardware such as monitors that you see in the photos there, or software, which is becoming increasingly relevant for cloud computing space that the testbeds are starting to use. And lastly, funding travel for forecasters to participate in experiments. So again, just want to reiterate, this support is critical for allowing testbeds to run their experiments or hackathons, and enables the testbed R2O projects to more efficiently move through the R2O funnel in preparation for hopefully successfully transitioning in the future into operations. Next slide. All right, and to wrap up the presentation today, I just wanted to end with some high-level thoughts about what our program is planning to do in the future. The first one I want to highlight is the Testbeds program is beginning to investigate how to integrate human-centered design into testbed operations. So the goal here is to ensure that the testbed's products and services are better aligned with the needs of the testbed participants. That can include researchers and forecasters, but also end users, both in the operational communities that are producing the forecasts and warnings, so our forecasters and WFOs and NSUP centers. But not only that, also the communities that are using the forecasts and warnings, such as the EMs, like we heard from earlier this morning, all the way down to the public. A great way to integrate the human-centered design concept into the testbeds will be through incorporating social science research into the testbeds going into the future. So as Castle mentioned earlier today on his great presentation, was that with WPO's recent reorganization, the Testbeds program is now part of the Science, Technology, and Society division, which is led by Gina Esco. And part of that division is also JTTI and social science, the social science program in WPO. So I think that new division structure really is creating a great opportunity to improve our coordination across WPO programs to better support the testbeds through concepts like human-centered design. And finally, the next WPO NOFO for FY25 is quickly approaching. I know that we just started FY24. We're still waiting to get our actual funding, but we are already starting the process of planning our next testbeds competition. And want to share this as an important opportunity for all of us to update the research priorities I shared earlier. Ultimately, those priorities will inform our new set of projects that will work with HOT over the next 3 to 6 years, most likely. So be on the lookout for more information later this winter as WPO begins our NOFO development process. So like I promised, a quick overview there, and that's all I have. So thanks for your attention. And I will turn it over to Wallace and Jason to give some updates about what's been happening in HOT over the last year.
All right, good afternoon. Thanks, Jordan, for the nice intro. I'm Wallace Hogshead, Science and Operations Officer at the National Hurricane Center. I'm speaking on behalf of Jason and I. Jason and I serve as co-directors of the Hurricane and Ocean Testbed. And the purpose today is really to set the stage for the next 4 talks. You're going to hear from the PIs of the 4 current HOT funded projects. And I want to give you a sense, to set that context, I want to give you a sense of kind of the actual work that we're doing in the testbed, because I think that'll give you a sense of kind of how we work with the PIs to increase the readiness levels, as Chandra talked about, getting these new innovations really close to the edge of going into operations. So before I go on, I want to say that this would actually be the last slide of my presentation if it weren't for the folks you see listed here. So we have an awesome team, 2 folks at CIRA. Alan Brammer serves as our IT facilitator, and John Martinez is HFIP model diagnostician. And we have a couple folks from Samantha and Stephanie who have been instrumental in kind of advancing, and they're part of TSB at the Hurricane Center. So this crew has been instrumental in advancing sort of the technology architecture that I'll talk about, as well as some of the projects that we've been working on. So awesome team, and it's great to have both the CIRA component working together with the Hurricane Center component. It provides perspectives that really accelerate these projects for operations. So thanks to that team. All right, so first things first, Jordan hit on this, but the organizations that fund us. So Jordan talked about WPO. We get a lot of infrastructure funding from them that help to support Alan and John. We also get funding from STI to advance critical operational milestones. And without that funding, we wouldn't be able to do what we do. So thanks a lot for that. Okay, so we've shown this slide a few times over the last couple of years. It's kind of a visionary slide. It used to be a visionary slide. Now it's very real. We've made a lot of progress. We've also gotten funding from some supplementary money that helped really lay the foundation in terms of the infrastructure you see in the pictures here. Progress in the virtual technology ecosystem, and you'll see a lot of that through the presentation here today. But ultimately, our goal is to take innovations that are being developed, incubated in the research community, and get them as close to the edge of operations as we can. So just a quick timeline in terms of what we've done this year. So last year, about this time in this meeting, I think Stephanie talked about our first hackathon we did last year. It was recon focused. We had folks from HRD, from NESDIS, all in the William LaPinta Laboratory at the Hurricane Center. And we were hacking away at trying to get some data sets into AWIPs, trying to design some new products to put in front of forecasters, getting forecasters' feedback. And I'll touch on the outcomes from that here in a little bit. In the spring, we kind of sat down and we set some goals. We had this new cloud AWIPs infrastructure, and we said, hey, let's try and get 10 new data sets from these various projects into cloud AWIPs. So we kind of set out the roadmap to do that. We also wanted to document how we do what we do, because that's going to help more people get involved. As an example, I didn't know the nuts and bolts of AWIPs, but our team actually taught me, and I was able to get a data set into AWIPs. So pretty cool. We're just trying to build the repeatability and the scalability, because as we grow, we need to have that in place to do these things faster and faster. So in the summer, fall, during the hurricane season, it was all about execution. We were trying to get data into AWIPs. We were talking to the PIs of all these various projects. We had another hackathon. I'll talk about that on one of the slides coming up. And we actually operationalized the outcomes from the previous hackathon. So I'll touch on some of these items. Okay, to me, this is one of the most important slides of the day here. There are a lot of other important things, but this is really important. So you don't have to look at all the details, but one thing I want to point out is just up at the top. So a development side of the workflow, a staging component of the workflow, and an operational component of the workflow. This dev staging ops kind of paradigm is common in the software development world. It's the way things are done. We actually didn't really have a staging environment to work in. So if you think about some new innovation that may be written in a certain way, a certain language, certain data formats, and then on the other side, you have the operational environment, which is the sacred, very secure, 100% uptime. You don't put things in ops that are going to break ops. So in order to really advance and iterate quickly, you've got to have this middle staging environment. And big kudos to Alan. I view him as kind of our technical architect of the test bed, and he helped us, along with GSL, kind of working together to get this technical environment in place. And this has been huge, and it's a huge foundational step that's going to help us move faster in the future. So really important. Again, there's a lot of details I'm not talking about, but really important. Okay, so how did we use this technical environment? So I'm going to give you, there are going to be a lot of pictures. It's late in the day, so I was thinking pictures would be the way to go here. So the hackathon. So during the hackathon, we prototyped 2 new configurations of tail Doppler radar data and WSRA and Kaya wave height data. We talked to forecasters and got their feedback on what's the way we need to view this data, what's the way we need to present it in AWIPS. During the hackathon, we kind of optimized this, and then we put it up in our repo and said, hey, this is ready for operational transition. I'm happy to say that as of about a month ago, our team and TSB successfully transitioned this into operation. So forecasters, anytime this data is flowing, they will be able to see it in the operational AWIPS environment. So it's an important milestone because we've demonstrated this end-to-end R2O pipeline. Just to give you a view of it here, this is the tail Doppler radar display. We've got kind of wind speeds near the surface, wind speeds in the mid-levels, a messy looking streamline plot, but if you look closely, you can see multiple levels. It's 3-dimensional data condensed down into 2 to get a sense for the tilt of a vortex in the structure. You know, we worked closely with HRD to kind of figure out what data we wanted to put in front of forecasters. One display gives them a 3-dimensional view of the data. We'll continue to iterate on it, but it's a great start. All right, and the other thing we transitioned, I mentioned WSRA Kaya. You're looking at wave height data plotted here, colorized by the magnitude. This is the exact same configuration that the satellite altimeter data is shown in AWIPS. So it allows forecasters to really quickly compare different instruments and in the same exact way that they do for other satellite instruments. So really exciting. These are operational. Next year, maybe we'll talk about 2 or 3 more things that went operational. Okay, Jordan, keep me honest on time here. I forgot what time I started. So, all right, the second hackathon. So this year we sat down halfway through. Awesome. So this year we sat down in the lab during Hurricane Idalia with a team from GSL in the room with us to deploy a fully end-to-end cloud workflow. So Avichal talked about the HAFS. Avichal and several others have talked about the HAFS ensemble being run experimentally on AWS. So we worked with EMC to grab the data off their cloud bucket. We ported it over to our cloud. GSL grabbed the data, post-processed it, and ported it into their DESI platform, which is a cloud-based analysis, visualization, and ensemble diagnostics platform built for decision support. So this is an example of some of the diagnostics that went into DESI. This is time of arrival based on the HAFS ensemble. So you can see kind of the colors changing to give you a sense of when the wind, tropical storm force winds will arrive. And then what you see down here is kind of a point-based diagnostic analysis of timing, intensity at an individual point. It's a dynamic environment. And the reason I wanted to show this, I think this platform has enormous potential. And some of the times when we hammer on the modelers about, hey, we need the spread and the skill optimized, you know, in order to really get the most out of this, we got to have not only the software lined up, but also, you know, the modeling systems ready to go so that we trust them and can message risk based on that. Really exciting. During the same hackathon, we worked on some JETI-funded surge product. Dave Zielinski talked about that a little bit, so I won't mention it here, but super successful. way to get things done and get them done quickly. We did this like in 2 days. So, all right, now I'm going to go through kind of like just a picture book of some of the data sets that we prototyped in the cloud, just to give you a sense of all the different projects and how we're working with the PIs. Tomorrow morning, we'll talk about a new wind speed probability model. We've been tinkering a little bit with this in the cloud just to make sure that it's compatible with the AWIP system. This is an example of Ryan Torn's project. He'll talk about it. He'll talk about some of the more advanced stuff that he's working on, but we had this data running in the cloud in real time all season. This is an example of a HAFS cycle in cloud AWIPs, multiple parameters all displayed at once for the forecasters. And this is an example of probabilistic wave data from the National Blend of Models that we prototyped in the cloud as well. On the recon side, you've already seen these two on the top. These are both in collaboration with HRD and NESDIS. This one in the bottom here is interesting. We've had some talk about 2D wind analyses. Well, there was a project, I think, led by John Naff that was accepted for implementation maybe 7 or 8 years ago. We've kind of picked up the ball on this now that we have this environment, and this is a 2D wind analysis that we're starting to prototype and look to see how we want to configure in AWIPs. On the bottom right here, this is a sample of IRAP data, which provides vertical profiles of wind all the way down almost near the surface. So another recon-based data set that we've been looking at. And then finally, on the satellite side, we have prototyped, actually it's more than prototyped, I think we have the data flowing in real time right now. This is the Tropics mission, and you can see a couple different channels plotted here. So this has been helpful just to, again, take it from the readiness level, 4 or 5 up to 6 or 7 pretty quickly. All right, last slide here. So looking ahead to 2024, we're 2 years old. We're building on a really strong legacy foundation from the Joint Hurricane Testbed. Frank Marks talked about this a couple days ago. We had a nice head start, 20 years of great work, and we're trying to take it to the next step through some of the ways I've talked about today. We're trying to build this machine. I've talked about the technical architecture that we've really been putting a lot of effort into, and some components of this machine, of course, science. All the R&D that's being done with our PI partners out in the academic and cooperative institute world. We're going to continue to focus on that. Everything I showed you has a connection to risk communication. Our mission is communicating risk, and so every data set helps, whether it helps us to refine the surface wind field, or it helps us get a little bit more uncertainty information about a forecast. That's the angle of science that we're focused on. Technical, I talked about this a lot. Really, this technical architecture that I talked about is about more closely linking the PIs to the HOT staff, the R2O facilitation staff, to the technical operations, our TSB group, all the way to the forecasters. We're trying to bring these groups closer together to make faster and more scalable and repeatable progress. And finally, I said it's a machine, but one thing that you can't engineer are humans. And so we're putting a lot of time into talking with all the PIs, building these relationships, because ultimately you can't build a machine without the people that are involved in the machine. So we're putting a lot of focus on that. And we're going to continue doing a lot of the things that I talked about, hackathons, working on this technical architecture. We're not finished. We might be 20% of the way there, but I think we're making great progress. And again, thanks a lot to the team and the folks who provide the funding to make this happen. So with that, I'm going to stop and hand it off to our first presenter, who I believe is Jonathan Vai. So Jonathan, take it away.
Okay, thanks very much, Wallace. Can you guys hear me okay?
Yes.
Okay, yes. So this project is about forecaster support products for analyzing tropical cyclone intensity and structure from aircraft recon. And I just want to give a shout out to my team. We have a really fantastic team, including Eric Hendricks and Chris Rozoff here at NCAR. Michael Bell and his students, Alex DeRosier and Jenda Hart at CSU, and June Zhang from University of Miami. And this is my first WPO project. I just want to say the support from WPO has been really great, especially Wallace at NHC has just been really great to work with. Lisa's our liaison with the forecaster team and the rest of the team there. So I have a lot of slides. I'm going to jump right into it. The motivation for this project, as you saw from the earlier presentation on JHT priorities a couple years ago, was how to deal with this conflicting situation. Sometimes the observations don't agree. And so when the forecasters are in their forecast cycle, they have to do the analysis of intensity and RMW and wind radii. And it can be really tricky because sometimes these data, as you can see, there's just a temporal plot there of data from Hurricane Sandy where the flight level data are the red triangles reduced to a surface equivalent. The blue triangles are SFMR, and the green line's in kind of an objective upper bound of the flight level data. And you can just see that sometimes these don't always agree. In fact, sometimes there's discrepancies where the flight level data may be pointing to 10 knots higher than what the ultimate best track was. And we know that a lot of this is related to uncertainty and how those winds reduce down to the surface. So that's a large part of it. But the last thing the forecasters need to do is have to be reconciling all sorts of observational data that are not agreeing. You know, there's NEXRAD and dropsons and SFMR and flight level data and other things. So the goal of this project is really to try to ease that process and come up with some objective ways of analyzing these. And just a couple examples of storms that proved challenging to analyze included Irma and Jose, to some degree Ian, and of course Dorian was another one. And you can just see here with Dorian, those blue triangles of the SFMR, the adjusted flight level winds using standard reduction factors are the red triangles, and there was quite a discrepancy. So you can see that the forecasters kind of split the difference in that case. But these are the type of cases, especially for these high profile, high intensity storms, that it would be really nice to have some better tools. So that's what this project is about. We're trying to improve the spatial and temporal analysis of the surface wind field. And so as part of this, we're implementing the observational analysis products. We're also going to be producing graphical and tabular outputs of the estimated Vmax and RMW and wind radii, so that the forecasters can analyze these more quickly and with greater confidence. And part of that is also going to be to include for the first time uncertainty bounds. So this project is not starting from, well, it's starting from a well-developed code base of 4 or 5 different capabilities. So one is the VDM dataset, the Enhanced Vortex Data Message dataset. Another is the Extended Flight Level dataset, Flight Plus, which is a research grade dataset. And then there's another code set being brought in called the Tropical Cyclone Observations-Based Structure Database, or TCOBS. And that is looking at the temporal aspects of analyzing these data. And then finally, Michael Bell's Samurai is also being brought in. And so the panel on the right just shows some Samurai analyses and radius height plane for Hurricane Michael in 2018. And the black line is the analyzed RMW. So you can just see that this tool is able to produce some very nice analyses, blending lots of data. Okay, the first task kind of followed through after my HFIP project from previously, but that was to upgrade the VDM plus dataset. And so with any data-hungry project like this, you need to have lots of development data. So one of the major tasks initially was to update the reader and basically be able to read the post-2018 format. So there were a lot of changes. They're summarized there, but they added a number of extra fields, including the center dropson surface winds and outbound leg maximum winds as regular items. So this was a pretty major code upgrade. And just to let users know, any VDM plus users, these variable name changes and whatnot are going to break your codes. So there's a lot of variable parameters that have been added and renamed, and some others that have been fixed. In terms of comparison to the previous version, the new dataset version, which we're calling version 2.0, adds 7 years of data. It's updated to the 2022 postseason best tracks. It's also updated to use the new extended best track dataset from CIRA. And also for the ship's development data set, there were a number of changes in that data set, as well as we also unpacked a number of variables that were previously not unpacked before. So that basically doubled the number of ships parameters, which was a lot of work. And then it also added 2,000 vortex data messages and about 100 storms to the data set. So this data set has now been released and is available for research use and public use there at that address. And soon, and then one of the upcoming tasks is to get this running in real time along with the visualizations. But an even bigger task is to kind of refactor the Flight Plus code set to support real-time flight level processing. And so the goal here is to take the same high-quality storm relative outputs that Flight Plus provides and provide these in near real time. And so work began on this back in August. And the first task was to set up the real-time data stream of HDOPS, which is now available for each storm. So if you click to the individual storm page on the TCGP beta test site, you can go read these HDOPS for the whole storm. And this is kind of a big task because the Flight Plus code set was really optimized for task decomposition and to do the quality control step by step as you process through the data. So that code set is set up to run in parallel for many storms at once on the NCAR HPC resources, and it produces 4 different levels of data products. And the new Flight RT, the real-time data stream, is optimized for real-time processing. It has only 1 entry point, and it writes out a single netcdf file that will contain all the outputs from all the different steps. And it's parallel to Flight Plus, and it's now highly modularized, which we hope will help make it easier to transition to Python later down the road. And just for those who are not as familiar, the HDOBs are really little files. They're 20 lines of data. Each line is typically a 30-second average for most of the parameters. And there's almost 9,000 of these for 2023 just for the Atlantic Basin. So it is quite a task just to organize these and get it into a form where you can run over very quickly, but we've now achieved that, and we can run really quick with low latency and minimal footprint. Just comparing the variables, we're going to try to keep the variables as much as similar to Flight Plus, but there are going to be a few differences that will, again, break people's codes if they were used to the old data set structure. But I just wanted to note that there's a number of Flight Plus variables that are not present in the HDOBs, so they're not going to be in a Flight RT. And those include the navigational parameters and some of the cloud liquid and microphysics type parameters. And so this is just the sequence of processing. There's an organization step where you get all the HDOBs into separate directories and files by storm and flight, and then you read them in, and there's a validation step that's optional, and then there's a quality control step, and you set up the initial output file, the netcdf file. And then there's a wind center computation step, and this is really important because we're going to be providing data in storm relative coordinates, and you have to do that reliably in real time. So that's one of the things that we just finished integrating into the code, and now we're moving on to the next steps, which will be parsing the radial legs and computing azimuthal means, etc. So Chris Rosoff is the team member who's been tasked with doing the wind center finding, and he's implemented the Willoughby-Jamal technique, which you can just see here. You apply a prominence method to the Willoughby function, and you get off candidate wind centers, and then you have to do a little bit more screening to find the true wind centers. And there's just an example of Katia. So next, we're going to feed these data from VDM RT and Flight RT into TCOBS, which is a high temporal resolution database of observed TC parameters. And the initial version back from 2016 computed an analysis based on exponential temporal weight functions. So observations that were closer to the analysis time were weighted more heavily. But the innovation in this project is that we're adding a 1D var in time algorithm. And Eric Hendricks is the person doing this. This is an alternative method of estimating the state, and it's similar to 4D var in that it minimizes a cost function over a time window, but it analyzes a scalar instead of a 3D variable. So this is just how it looks like in terms of the math. There's a cost function that gets minimized. There's a forecast model, which in this case is an exponential curve fit to the observations in the time window. And there's just an example of how that would work out if you have 1 background value and 6 observation values in a time window. And on the left here, you can see the old method, the exponential weighting method. On the right is the 1D and VAR method. And you can see that they're pretty similar. The 1D VAR method is able to pick up on shorter term fluctuations, so it's a little bit less smoothed, I believe. And there's an example for the wind radii for Hurricane Katrina in 2005, applied for each quadrant of the storm. And so, so far this work has been completed in terms of the 1D VAR method is now in the code. It's been functionally tested and it's been evaluated for some case studies. And next we're going to be implementing it for RMW in position and then running for a 30-year data set, or the whole entire historical database, and then implementing it next year. So still ahead is to work on improving the specification of the observational errors. So lastly, I'm going to talk about CSU's side of the project. They've been working on a flight level wind reduction parameterization. And so this has been taking the Flight Plus data set and normalizing it into a polar grid space, where essentially you normalize radius by the flight level RMW, and then the azimuth is normalized such that the storm motion vector is at the top at 0 degrees. And this allows them to crunch through lots and lots of data, and they've been training a neural network to learn how to better predict the wind reduction factors. So here's an example for Irma, and as you would expect within the radius maximum winds, you can see where the SFMR surface winds are higher than the co-located flight level winds above it. That's what you would typically expect in a strong storm, where you may have an overshoot. And here's an example where they've used their model on Idalia TDR data. So they took TDR data from a NOAA P3 flight, and they fed it into Samurai, and then into a neural network to predict the surface wind speed. And so the pattern of wind reduction is consistent with the northward storm motion and wind asymmetry that you would expect. But the current model underpredicts the wind ratio a bit. So they're looking at some other techniques for how to do this. But this kind of just gives you a flavor of the type of resolution and detail that we hope to provide in the spatial wind analysis. And then lastly, they've been working on validating this methodology with dropsondes. So the way that they're doing that is taking the PC drops data set, where basically you get a flight level wind field from the merged TC radar analyses. And then you do some smoothing based on wave number 0 and 1 or 0, 1, and 2. And then they are mining the analysis to get predictors and projecting the original and smooth flight level winds down to the surface. And then for comparison, they're looking at the Franklin et al. 2003 method, where basically you multiply the flight level winds by 0.9 in the inner core and 0.8 at when you're twice the RMW. Well, technically it was outside the eye wall, but for this purposes, they're using twice the RMW. And then they're comparing these. And so this is kind of almost to the end here. On the top, you have tropical storms. The middle row, you have hurricanes. On the lower row, you have major hurricanes. And then going from left to right, the columns are no smoothing, and then wave number 0 plus 1 and 2, wave number 0 and 1, and then the Franklin et al. Wind reduction technique. And of course, dropsondes are noisy. There's always going to be some large errors. But basically, red are where the prediction error is positive, and blue is where the method is under predicting. And so you can see that the largest errors tend to be left of the motion vector, but they're also better than a radius-only method. So the Franklin et al. Method works pretty well as a baseline, but it looks like we're able to improve over that. And so they're going to be trying even other methods and trying to correct for biases that they're seeing in the dropsonde validation. So putting it all together, the next steps of the project are to get all of these capabilities running in real time. We're close to having some Flight RT capabilities running, and we're excited about getting all of this up and running, but this is the way that it's going to work. So eventually we're going to have all these input data streams available and being processed, and they're going to feed in to both Flight RT and Samurai. And then some additional information will feed into TC-OBS to get the temporal outputs. And then we're going to have both spatial imagery plots for NHC, as well as the temporal analysis of how these look in time. And there will be a netcdf file that's also provided to be able to feed these into AWEPs. And then we'll have some text files with tabular outputs of the intensity, RMW, and wind radii for NHC. So we welcome feedback on this project. There's also a lot of opportunities to collaborate on the science from these data streams, and thank you very much.
Thank you, Jonathan. A really, really complex project with a lot of potential. So we're excited to work with you on that. All right, next up, Mark DiMaria. We'll talk about a new machine learning model.
Oh, thanks. Thanks, Wallace. How do I turn the slides? Oh, with this.
Right here, and then Red will go back, and that's the pointer.
Great, thanks.
Whenever you're ready.
Okay, yeah, go ahead.
All right. Oh, you did share the slide.
Okay, well, I'll go ahead and start here. This is a hot project that we're just starting into our second year. And the purpose is to try to use machine learning to estimate forecast uncertainty, both in terms of track and intensity. And the Colorado State has a very strong machine learning group, AI group. So we've teamed up with a couple people from the Atmospheric Science Department, Libby Barnes, her postdoc, and then also working with a group at CSU. Green one moves it. This green one? No. This one?
This one right here.
Yes,
Looks good now. Thank you.
that's better. Okay. So a quick outline. I'm just going to give a little bit of motivation. I'm going to and then talk about the error prediction model. I'm going to concentrate on some results from 2023 as with an independent test, and then talk a little bit about where we're going after that. So this is a NHC products page for Hurricane Ian. And there's a lot of graphical products that you see on this page, and all the ones that I've circled include probabilistic information, which is more than half of them, including the storm surge products with the P-surge model, wind speed probabilities, the arrival time. But the one of the maybe limitations is that nearly all of the uncertainty in all these products comes from climatological error distributions. There's very little dynamical model ensemble that goes into any of these products. And the reason is that these have to be consistent with the NHC official forecast. For example, if you took the GEFS, sometimes all the members of the GEFS are outside of where NHC is forecasting. So it would look a little odd to have no probabilities of hurricane winds along the NHC forecast track. So it's essential to have uncertainty information in the products, but also consistent with the NHC official forecast. So that was the motivation for this project. So the idea is that can we use machine learning to take ensemble information and use that, train it against the NHC forecast errors, and come up with a way to have uncertainty information based on ensembles, but consistent with the NHC forecast. So you kind of think of this as a way to project ensemble information onto the NHC errors. I'll just show this graphically. I think it's an easy way to show it. This is a neural network model, and this was a method that Libby Barnes from CSU came up with. The idea is that you have a bunch of input. It could be forecasts from a bunch of different ensembles. Sometimes the errors are a function of the synoptic situation, like HFIP might work better in high SSTs or low shear. And so there's also some environmental information. And so what the neural network does is it's trained to predict all the parameters of an assumed error distribution. And in this case, the SHASH distribution is used. It's like a normal distribution, except for that it allows for skewness. So the errors might be bigger on one side than the other. For track, it turned out that we tried some different things, and the kind of the old-fashioned bivariate normal distribution seemed to work as well as anything else. So in this case, the neural network tries to predict the 5 parameters of a bivariate normal distribution. So version 1.0 of the model, which we're tested this year, we took four models for track, 4 models for intensity, deterministic models. So it's a multi-model ensemble with 4 members. The reason we picked these is because we had a long training history. And so there's 4 predictors as well as some storm environmental predictors like vertical shear and SST that comes from the SHIPS model. The output are the parameters of the track and intensity error distributions, and also a number of graphical and text products. And this was trained on a 10-year sample, and then 2023 was completely independent runs. This was the kind of a first draft of one of the track products that was produced by TCane. And this is for Hurricane Ian. And we showed this to Pablo and Wallace when they came to visit Sierra. And Wallace had a great suggestion to try to relate these to the climatological error distributions. And so trying to figure out how to have color scales that showed this distribution and the climatological error distributions was a nightmare. So they suggested something simpler. So what we ended up showing is just the 67th percentile, similar to what's used to make the cone graphic. It might not show up well in the back, but the solid lines are what TCane predicts for the error distribution at through 5 days, and the dashed line is climatology. So this forecast, particularly approaching Florida, was saying that the errors were a little easier than climatology. Actually, this is Idalia. This is not Ian. Too many ice storms hitting Florida. But it was basically showing, this is early in the forecast of Idalia, and early on when the system was disorganized, there was kind of divergence in the track models, but eventually they converged, and the later forecasts were actually easier. A couple of the intensity products. This is shows the error distributions at different levels. There's the 25th percentile, 75th percentile, and so on. If you just look at the right side, that's a prediction of the NHC intensity forecast error. The black line is the NHC official forecast, and the red line is the median of this predicted distribution. And basically this shows why you need skewness. This is showing that it was a lot more likely that Idalia was going to be stronger than what NHC forecast, and that turned out to be the case. Some of the other products is looking at the probability that Idalia was going to be a Category 1 storm, 2, 3, 4, and 5, out to 5 days. And then the dash line is the same probabilities based on climatology. So again, this shows that there was a much higher chance than climatology that Idalia was going to be a hurricane. The initial intensity here was about 35 knots. It was early in the storm. Since we have the entire error distribution, we can also extract the probability of rapid intensification using the same thresholds that's in the SHIPS model. This is, again, from Idalia. Very little chance initially, with the probabilities becoming higher later. So the verification, I mentioned that it's trained on 10 years worth of data. We ran this, unfortunately, not quite in real time, but we did run it after the season. This includes all the cases through the end of October. So about a little more than 300 cases in the Atlantic and a little bit less than 300 cases in the East Pacific. So looking at 2 verification measures. The first one is just reliability. So we're producing these error circles. And so you can just basically, for example, if you take the 80% circle, did 80% of the actual verification, or 80% of the cases actually fall in that circle. And we do that for track and intensity. And then we also look at the error spread relationships. So when TCane expected has a wide distribution, were the NHC forecast errors bigger in general? So those are 2 things we looked at. This just shows how we calculate the reliability. I think I'll skip that. I think it's pretty clear how we do it. You just see if the NHC forecast error was inside or outside the circle, or inside or outside the 80% area from that diagram on the left. So these are the results. I did these for individual hours, but just in interest of time, I'm just showing the summary statistics. If you look at the red bars, that's the 80% interval from TCane. And so the dashed line is 80%. And if it was absolutely perfect, those red bars would exactly touch the dashed line. And it turned out for intensity worked great. I mean, it was very well calibrated. It was a little tiny bit under. East Pacific track worked great. We looked at two of the intervals, 67% and 80th. Atlantic track was kind of weird. It basically was way overconfident. What that means is that when that number is low, a lot more of the NHC forecasts were outside the circle than we're supposed to be, or the ellipse, if in the case of track. And so I think John Cangelosi showed in the at the beginning that the track errors for NHC were pretty big this year compared to the long-term history. So, okay, looking at the error spread relationships, again, it's just comparing what happened. I'll just show these quickly. This is for intensity. We took the interquartile range as just one of the boundaries, the 75th to the 25th percentile. And then we just stratified the NHC forecast errors and made box and whisker plots. And you can see there's a pretty systematic increase in the errors as you get from the lower tercile to the upper tercile. So the biggest errors were when TCANE thought that the errors were going to be big. And the median also goes up pretty systematically. So pretty happy with the intensity verification. E-specific track, very good, very monotonic relationship. The Atlantic track, not as good. There is an increase in the median, and again, the worst of the forecasts were in the upper third, but it's not quite as clear cut as the intensity or E-specific for the Atlantic. Finally, I've got the you can look at summary statistics, but it's good to look at the individual forecasts, and so I decided to go ahead and look at Philippe, since we talked a lot about Philippe. This is right before that black line is the best track, and the TCANE realized this was a hard forecast. After 48 hours, those ellipses are huge because the models diverged, which is good. But what happened about 72 hours, it got very confident. It thought, well, I know where this is going. So what happened was that I looked at the individual track forecasts from the models, and they diverged very quickly at the beginning, but then they all kind of ended up in the same place, and they were all wrong. So in this case, I think this is one of the reasons that the model was overconfident. It tended to do that more. So one of the very first things we're going to do is impose time continuity. I think this is kind of a showstopper for the forecasters if they would not know what to do with this at all, if having a short-term error prediction being much larger than the long-term prediction. So summary and next steps, I think the results for 2023 were pretty successful. We uncovered some issues with the time continuity. For next year, we're going to add the time continuity constraints. I've already working with the machine learning group, coming up with ideas there. Because there's a good relationship with the terciles, one of the things we're going to do is put this into the wind speed probability model, so that we're going to test to see if we can put the ensemble information and get it to feed directly into the wind speed probability model that produces a whole bunch of operational products. We may try this also to predict wind radii errors. Of course, we have to go to HAFS next year. We got kind of lucky that HWRF was ran one more year, but we do need to get the HAFS information in there. Do this on the West Pacific as well. So just kind of a summary slide. I don't know how these show up. I think one of the ways that we can use this type of machine learning is that on the left side of there is you've got all these different ensembles, and you can produce all kinds of interesting ensemble products that are good for the forecasters. But on the right-hand side, like I mentioned at the beginning, you don't want to have forecast probabilities that are inconsistent with the NHC forecast. So you could take whatever ensemble members you have, put it through machine learning to project it onto the NHC errors, and then you could create a whole of whatever products you want, consistent with the ones that are already produced. But it puts the ensemble information through machine learning into the NHC public-facing products. And then I do have 1 minute left. We have another HFIP funded project that I wanted to mention. It's kind of related to this project and what Wallace is going to talk about for Pablo tomorrow, is that we also need to look at wind gusts. It'd be nice if there were wind speed probabilities for gusts for use by the WPO. So this is a 3-year HFIP funded project to develop a gust parameterization for the HAFS model. And June Zhang and Andy Hazelton already have this, at least the first version, working in HAFS. And on the top is the gust factors for Hurricane Ian. And we have a huge verification data set from ASOS and WeatherFlow that we're comparing against. This is the European Center gust parameterization. And if you can't see the scale, these look good. If you can look at the y-axis, the HAFS gust factors are way bigger than the observations. And so, directly using the ECMWF gust parameterization, it's not directly appropriate for it. So like step one is try it out of the box, see how it works. Qualitatively, it looks good, but quantitatively not good. So they're going to work to tune that. There's parameters, there's tunable parameters in that European Center gust parameterization that we hope to come up with that. And the idea is to eventually maybe have probabilistic products for all of the, that include sustained wind and gusts. Okay, thanks.
All right, thank you, Mark. Another exciting project getting us into the AI world. So next up is Ryan Torn from University of Albany. He's going to talk about the kind of a follow-up to a previously funded project on ensemble sensitivity. So Ryan, over to you.
Thank you, Wallace. Again, my regrets for not being able to be at the meeting today, but this is a follow-up, as Wallace said, to a previously funded project, and a follow-up to the talk that I gave earlier on Tuesdays as well. So obviously this is a hot funded project, but I want to say that some of the early ideas for this project were HFIP supported as well. So I want to acknowledge that. So we're going to go to the next slide, please. So I already talked a little bit about sensitivity analysis and what it can do to identify where you should go and observe. And so as I described in my talk on Tuesday, is that some of our early work was reducing tropical cyclone track forecast uncertainty. But one of the nice things about this ensemble-based sensitivity methodology is that it's not limited to just track, and it could be expanded beyond track into other things like intensity or even TC-related hazards like the wind and the precipitation field. And so if you go to the next slide, please. So the goal of this project was to expand the ensemble-based sensitivity package that we developed in the previous JHT-funded work to calculate the sensitivity of other metrics, including intensity, wind speed, and precipitation forecasts. And so we had some tasks to develop what are some appropriate metrics for doing that, producing daily real-time products that NHC could use for aircraft drawing using ECMWF and GEFS ensemble output. I'll talk maybe about some ways to extend that in the end. And then we brought, basically this led to a development of version 2.0 of this Python-based software that has this capability, with the ultimate goal of one day providing guidance that you could develop new aircraft sampling strategies that would reduce the hazard uncertainty rather than just track. Next slide, please. So talked about this on Tuesday. The ensemble-based sensitivity technique is just linear regression between some ensemble estimate of a forecast outcome and some ensemble estimate of a forecast field at an earlier time. The previous work, our forecast outcome, J, is some measure of the track. But what I'm going to talk about in this talk is our forecast outcome is some measure of the storm intensity, or the storm wind field, or the storm precipitation field. And here the independent variable is some model field that you want to compute the sensitivity to. Now for track, that was pretty straightforward to do because we believe that track is mostly governed by the steering flow, which is some layer average wind. When you start going to intensity, or the wind field, or the precipitation field, it becomes a little more complicated because there's more model fields that you might think is that forecast is sensitive to. And so one of the things we had to do was kind of do some early work is to figure out what was that appropriate set of fields for each of these metrics. Next slide, please. So as I said on Tuesday, since 2018, NHC forecasters have been using the ensemble-based sensitivity guidance for drawing G4 flight tracks. This has been utilizing this time-integrated track metric, which is looking for the perturbation in the ensemble forecast that explains the most variance in the track. This particular forecast is from Hurricane Ian, and here it's showing that the perturbation track is a storm that is making landfall further south down the Florida coast and is moving faster. And for a lot of the operational products that were produced last year for this is the metric that was used. And so what I'm going to show coming up now is some of these experimental products based on the intensity, the wind field, and the precipitation field for Hurricane Ian last year for this particular forecast. And I'll also show some examples of some real-time products that we produced this year for Hurricane Idalia. Next slide, please. So going back to the real-time products for Ian last year, this is the sensitivity. The shading here is the sensitivity of Ian's track forecast to the steering flow vorticity at a time when where there was the desire to have a G4 flight track. So again, warm colors here mean that if I increase the vorticity at that point, I'm going to get a track that is more to the south and faster than the ensemble mean track. And the dot is where Ian is predicted to be at this time, and the dashed is the vorticity. So you have a big anticyclone sitting east of Florida at this time. And so it says if I weaken that anticyclone to the north of Ian, I'm going to get a more track further to the right. And if you go to the next slide, sorry, that's my mark on there. Next slide, please. One more click, sorry. The next slide, there we go. There we got the drops on points for the G4 mission. And you see it's doing a couple of circumnavigations of the storm. And then there's substantial environmental sampling on the north side in the eastern Gulf of Mexico, which overlaps with that sensitive region. Next slide, please. All right, so let me talk a little bit about the forecast metrics that we've developed. The goal here being trying to have this be run with as little forecaster input as possible, knowing that forecasters don't have a lot of time to do these. So for intensity, we use something very similar to track in that we're looking at a time-integrated intensity distribution based on empirical orthogonal functions. And so the figure on the left is each ensemble member's intensity. Black is the black solid's the ensemble mean, and then the dashed is the perturbation, which is what the metric is based off of. In this case, we have a forecast where Ian's predicted to become deeper and last longer than the ensemble mean. For the wind field, we developed a two-dimensional automated metric that basically draws out where could you have winds along the forecast track. And so it adaptively figures out the domain. And that's what's denoted by this thick gray line here. And then it does an EOF decomposition of that wind field. And so in this particular case, it is higher winds on the eastern side and off the Florida coast, lower winds on the western side. So it's essentially associated with an eastward shift in the track. If you want to, I can answer a little bit more about the automated procedure a little bit in the Q&A session. Next slide, please. For precipitation, we use something very similar. We also have an automated algorithm that figures out where is the greatest precipitation over land over a period of time, then narrows it based on looking for 24-hour periods, and then draws its own automated area and does an EOF decomposition. So in this particular case, the metric area is the Florida Peninsula. That's where we had more than a half an inch in 24 hours predicted, and then does an EOF decomposition. In this case, the metric is greater precipitation over the I-4 corridor. So next slide, please. So I want you to keep those metrics in mind. And so what I'm going to show is a number of paired figures here. On the left is always going to be the track sensitivity along with the dropsons. Whereas on the right is the sensitivity of the steering flow, the sensitivity of the intensity forecast to the steering flow. There we go. So in this particular case, I already talked about the track. For intensity, it's saying that if I strengthen the subtropical ridge to the north of Ian at this time, right around about 24 north, I'm going to get a stronger storm in the forecast. Well, what that's doing is by strengthening the subtropical ridge, you delay the landfall timing of Ian, and so it has more time to intensify before landfall. And you see that that sensitive region more or less overlaps, at least with the northern part of the drop zones for this particular case. Next slide.
5 minutes.
Thank you. Now I'm swapping out track for the wind speed metric that I showed before. And you see that overlaps very closely to what the track metric was. And again, Dropson's doing a very good job covering that sensitive region. Next slide, please. Here's for precipitation metric. Again, a lot of overlap in the sensitive region, that's subtropical ridge, but maybe a little bit more on the western side for this field. Next slide, please. This just shows an example from Hurricane Idalia of this particular year. Here is the wind metric, again, drawing out a broad region over the eastern Gulf of Mexico and going into the western Atlantic as the storm recurves. Right-hand side is the sensitivity of the wind metric to the steering flow, again, showing that if I strengthen the subtropical ridge to the east of the storm, I get stronger winds on the western side of the wind swath. Next slide, please. This is for the precipitation metric for this case. Here it's drawing out a domain that's over the southeastern US. Again, adaptively done, no human intervention had to be done here. And the sensitivity again is in the subtropical ridge to the east of the storm at this time, with the eastern edge of the drop zone sampling that sensitive region. Next slide, please. One of the big things is that there's a lot of data overload potential here. There's now 4 different metrics, multiple fields for every metric. And so I've been working with both Wallace, Alan, and Philippe Papin and Lisa at the Hurricane Center to kind of, how do we come up with a dashboard way that whoever is drawing these flight tracks can quickly look at all metrics and all fields simultaneously and try to figure out where's the best place to deploy to draw the flight track. And this is the prototype that we've developed. So each one of these each panel, I should say, is a different metric. And each color region in this paintball type plot is the sensitivity that exceeds a certain value. And so you're really looking for where do these sensitive regions overlap on top of each other, and use that to draw the flight tracks. And we've got some prototype Python packages that can allow the forecaster to go back and forth and draw and see how well it goes on there. And so I think we're really converging on this, but more work needs to be done. So this is from that Ian forecast that I just showed before. Next slide, please. So let me just summarize this up, is that it's shown that this ensemble sensitivity can be extended to calculate sensitivity of track and hazard forecasts. We've developed some pretty robust automated wind and precipitation metrics. We were able to run this successfully for all storms in 2023. In most cases, we saw that the hazard metric sensitivities were sensitive regions were overlapped with the track pretty closely. And so what we're going to be continuing to work on is refining that dashboard based on NHC and also WPC input, since they have the rainfall. We'll be doing some transitioning of the code to NHC for further testing. And I have a graduate student who's going to be working on some case studies. And I'll add that one of the exciting things that I've seen in this meeting is the ability of the HAFS ensemble also offers a really interesting way to extend this work. And so I want to get that output into this code as well. So thank you.
Thank you, Ryan. All right, our final presentation of the day is actually a recorded presentation because Sarah Ditchek is on leave. So Sarah's at CMUS and she'll talk about some HAFS sensitivity experiments she's been running.
You may have to load this. It's a little weird when you're sharing videos to have the audio. Okay, so it's going to work. Where's it? Okay.
Scientist at CMAS affiliated with HRD.
Starts it over.
Hi everyone, my name's Sarah. Hi everyone, my name's Sarah Ditchick, and I'm an associate.
It's not mirroring to the other screens, but is it sharing remotely? Yeah, it's sharing to the remote, but not mirroring to the screen. Don't know why. There we go. There it is. All the PowerPoints were open in the back. If we just had everybody use Google, it would be fine. I'm thinking about it. All right. That was a special case. Yes.
Scientist at CMAS affiliated with HRD. You're hearing a pre-recorded version of this talk since today happens to be my due date, and I'd rather not leave whether I can present up to chance. My collaborators include Ryan Torn and Lisa Bucci, and my point of contacts include Jason Sippel and Wallace Hogsett. And they should be at HFIP so can answer any questions that come up and send any follow-ups my way for me to tackle after maternity leave. Okay, so let's jump right into the motivation for this HOT project.
Yeah, I know.
It all started with the fact. Hi everyone, my name's Sarah Ditchick, and I'm an associate scientist at CMAS affiliated with HRD. You're hearing a pre-recorded version of this talk since today happens to be my due date, and I'd rather not leave whether I can present up to chance. My collaborators include Ryan Torn and Lisa Bucci, and my point of contacts include Jason Sippel and Wallace Hogsett. And they should be at HFIP so can answer any questions that come up and send any follow-ups my way for me to tackle after maternity leave. Okay, so let's jump right into the motivation for this HOT project. It all started with the fact that NOAA's G4 flight track strategy changed in recent years. I'll be using this plan view schematic to show those changes. In 2017, the typical G4 surveillance pattern was just one outer ring circumnavigation around 330 kilometers from the TC center, as well as environmental targeting as described by Aberson 2003. Beginning in 2018, the G4 began to conduct an additional circumnavigation at around 165 kilometers when possible. This change was based on research that suggested that sampling the near-storm environment would lead to forecast improvements. Implemented operationally in 2019, environmental targeting conducted by the G4 began to be guided by Ryan Torn's ensemble sensitivity metrics. And these three components still make up the current G4 flight track strategy. For brevity, I'm calling the environmental targeting the non-standard pattern as it changes based on the ensemble sensitivity metrics, and I'll also be calling the two circumnavigations the standard pattern, split into the outer and inner circ. The impact of these changes on TC forecasts need to be quantified, and ways to further optimize the strategy should be assessed. These results and optimizations can then be delivered as guidance to HOT and NHC for use during G4 flight track planning. For example, let's say the non-standard G4 patterns are most impactful when flown in a tropical storm, but are not as impactful when flown in a hurricane. Well, then the guidance delivered will indicate these distinctions. That brings us to this project. The objective of the project is to quantify the impact of G4 recon on TC forecasts of track intensity and significant wind radii by using HAFS to assess impact of the G4 overall, of the G4 non-standard pattern, and the G4 inner circ pattern. Again, given the numerous changes over the years, a comprehensive assessment of the current G4 pattern is needed. To address the objective, I'm running 4 experiments. The first is the control. It's HAFS out of the box. It assimilates all operationally assimilated conventional recon and satellite data and is called all R for all recon. What you see here is the typical C-130 alpha pattern in red, the typical P3 butterfly pattern in blue, and the typical G4 surveillance pattern in green, which you saw on the last slide. The second experiment removes the G4 recon data entirely and is called no G4 for no G4. As you can see, there is no green line on this graphic. The third experiment only removes the non-standard G4 recon data and is called no NS for no non-standard. As you can see, the only part of the G4 pattern is the standard pattern. The fourth and final experiment only removes the inner circ G4 recon data and is called no IC for no inner circ. As you can see, the only part of the G4 pattern that remains is the outer circ and the non-standard pattern. When conducting studies like this one, having the largest sample possible is ideal given variability that's present from forecast to forecast, TC to TC, and even year to year. So I identified every TC between 2020 to 2023 that had tasked G4 missions, and in total there were 16 TCs, all in the North Atlantic Basin. This table lists only 15 of those 16 TCs by year, since one TC, Ada, didn't have existing GFS input data. This resulted in 478 cycles with 56 total missions. All missions have non-standard patterns, and only 35 have an inner circ pattern. Experiments for 2020 to 2022 have completed, so today I'll be showing you results for that 3-year sample, highlighted here. The model used for these experiments is HAFS-A. This model was chosen after verification comparisons were performed between the HAFS-A and HAFS-B 3-year retrospectives. Again, I'm going to be denying TC recon in 3 experiments, no G4, no NS, and no IC. And to do that, I had to manually partition all recon data for each of the experiments. So what's coming up next? I'll be covering results for North Atlantic Basin TCs that had tasked G4 missions from 2020 to 2022. I'll be looking at track, Vmax, Pmin, and the significant wind radii, that's R34, R50, and R64. I'll also be following NHC verification rules and including cycles in a given TC from the first cycle with G4 recon through the last cycle run for that TC. I'll be using 2 new metrics detailed in 2 recent WAF papers, the consistency metric and relative impact methodology, and I'll touch on those 2 metrics briefly in their relevant sections. And finally, I'll be sharing results from various stratifications of the full sample, forecast with G4 recon, forecast without G4 recon, and those 2 stratifications stratified by initial classification. Let's talk about some of the takeaways you'll be seeing in this presentation. First, I'll be looking at the overall impact of the G4. For track and intensity forecast, directly sampling hurricanes was found to not be beneficial, and degradation also occurred in hurricanes when G4 recon was assimilated in prior cycles. For size forecast, G4 recon was generally detrimental as well. Possible reasons for these results could be the DA sophistication in HAFS and the HAFS version used, and stay tuned for a slide with more details on these 2 reasons. I'm also looking at the relative impact of the non-standard and inner circ G4 patterns. Overall, minimal impacts were found. And when stratifying down by initial classification, while minimal impacts found were mostly driven by hurricanes. Possible reason for this is that minimal G4 recon was actually removed relative to the C130 and P3 and remaining G4 recon that was assimilated. Now let's first quantify the overall impact of the G4 on TC forecasts. And to do that, I'll be comparing the consistency metric scorecards for 2 experiments, all R and no G4. Now, the consistency metric is a newly created metric that applies thresholds to the MAE skill, median absolute error skill, and frequency of superior performance to identify consistency in results. And we did this because only relying on the MAE skill can lead to a misinterpretation of results if the sample is skewed, which it often is. For more details, see my recent WAF paper at the QR code on this slide. For track and intensity, G4 recon generally improves tropical storm forecasts, but degrades hurricane forecasts. You can see that here below. These are consistency scorecards for this full sample stratified by G4 recon availability and initial classification. Tropical storms are on the left and hurricanes are on the right. Forecasts with G4 recon are on top, and forecasts without G4 recon are on the bottom. Gray transparent shading indicates those lead times where the sample size is less than 25. The x-axis is forecast lead time, the y-axis is the variable, and at each lead time, colored boxes relate to the color bar on the bottom right, where greens indicate improvement and reds indicate degradation. As you can see, G4 recon generally improves TS forecasts, particularly for those forecasts with G4 recon. You can see that at short lead times and more prominently at long lead times, despite the small sample size. But for hurricanes, there's mostly degradation present. And we can dig into these signals and see whether there were TCs that drove these results. And those signal drivers are now found here overlaid on each of the consistency scorecards. For tropical storms, Laura, Ian, Elsa, and Fiona drove the improvement, while for hurricanes, Fiona, Delta, and Sam drove the degradation found. Now, relating these results to previous work, the direct track results do align, while the direct intensity results do not. For track forecast, we found that retaining synoptic dropsons led to improved track forecasts in weak TCs, like tropical storms. Here, G4 recon, which is often in the synoptic environment, did lead to improved TS forecasts and also neutral hurricane forecasts. But we also found that removing synoptic dropsons degraded Vmax forecasts. Here, when we removed G4 recon, which is often in the synoptic environment, we actually found improved forecasts. So these results suggest that while the G4 is beneficial for tropical storm forecasts, directly sampling hurricanes with the G4 is not beneficial, and indirect degradation also occurs in hurricanes in cycles with no G4 recon. There are two potential explanations for this result. The first explanation relates to the DA sophistication in models. Recent research has found that the impact of recon on TC forecasts is strongly dependent on covariance choice. An example of this from one of my recent papers is given here. This shows the impact of dropsons on TC forecasts stratified by covariance used. On the left are those forecasts that used HWRF cycled covariance, and on the right are those forecasts that used GDAS covariance. And these are the consistency metric scorecards like the ones you saw on the previous slide. The x-axis is the forecast lead time, the y-axis is the variable. And as you can see, nearly all of the impacts from dropsons were realized when HWRF cycled covariance was used. When GDAS covariance was used, mostly degradation and neutral impacts occurred. And this result reinforced the importance of using covariance derived within the model rather than global covariance for DA. Now this project uses HAFS, and HAFS uses 4D and VAR with 3 hourly 80-member GDAS ensembles. So forecast degradation in hurricanes from G4 recon might indicate a non-optimized DA system. The second potential explanation for why degradation was found is the HAFS version used. Jason Sipple has been conducting some ad hoc experiments to look at the impact of recon on TC forecasts as a function of HAFS version used, and he found that the impact greatly differs based on the version, with HAFS B outperforming HAFS A. Now this project uses HAFS A, and this was chosen based on the 3-year retro performance. So these results might differ if rerunning experiments with HAFS B, and this is an option we might pursue if there are resources available to do so. Now, I don't have time to show you the impact of G4 recon on TC size forecasts, but overall, degradation was found, and this is perhaps due to the same two reasons as given on this slide. So now let's quantify the relative impact of two G4 patterns on TC forecasts. And to do that, we first compare these 3 experiments on the left to the same baseline, the experiment without the G4 recon on the right. This gives us consistency scorecards like we saw in the previous slides for each of the 3 left experiments. What we're interested in is the relative impact of these 2 sensitivity experiments compared to all R. In other words, how does removing the non-standard pattern or removing the inner circ pattern compare to having both patterns there? Now, I don't have time to get into the methodology for that, but it's detailed in a recent paper in WAF that you could find at the QR code on this slide, and Jason can answer any questions about that. To understand the relative impact of the sensitivity experiments, we're going to be using what we call relative impact scorecards. And I'm just going to be discussing results at short lead time, since removing either the non-standard or inner circ pattern generally does not impact TC forecasts at long lead times. Overall, minimal impacts were found if removing the non-standard or the inner circ pattern. You can see that here in these relative impact scorecards that take the full sample and stratify it down by G4 recon availability. The x-axis is that stratification and the y-axis is the variable. The colors correspond to the relative impact color bar in the bottom right, where purples indicate improvement relative to all R and blues indicate degradation relative to all R. Overall, removing the G4 patterns lead to minimal direct and indirect improvements. What I'm not showing is that when stratifying these results by initial classification, these minimal impacts are mostly driven by hurricanes. The question is, why might there be such a minimal impact if removing these 2 patterns? Well, it might have to do with the fact that there are minimal differences between the assimilated recon in NONS and NOIC and the number of assimilated recon from the rest of the aircraft. What you're seeing here is a radius on the x-axis, number of assimilated obs on the y-axis, with various different lines here for the all-R experiment. Each of the different lines corresponds to a different type of recon observation that was assimilated. For all R, you could see that about 3.1 million individual observations were assimilated across the sample. Now what you're seeing are the difference between the number of observations in all R and the number of observation in each of our sensitivity experiments. No NS in the middle and no IC on the right. And what I've included in the legend are the differences for each of the individual recon obs, but I really want you to focus on the numbers in the top right of each of these graphics and the percentages as well. So you could see that the differences between the number of observations assimilated in all R compared to our sensitivity experiments is quite small, under 200,000 observations in each. And so there's still a lot of recon data that's being assimilated into these runs. And so perhaps that's why we see minimal impacts when removing the G4 obs. Now to summarize results. I ran 4 experiments covering North Atlantic Basin TCs with past G4 emissions between 2020 to 2023 in order to quantify the impact of G4 recon on TC forecasts of track intensity and significant wind radii. The experiments were run using HAFS-A, and it assessed the impact of the G4 overall, the G4 non-standard pattern, and the G4 inner circ pattern. I'm leaving my takeaways for the 2020 to 2022 3-year sample here. Again, I'll be adding 2023 to the sample and reassessing these takeaways. Thank you so much for listening. If you have questions, you can ask my collaborators or point of contacts there, and you could also shoot me an email that I'll get to when I'm back from maternity leave. Thanks so much.
Sarah, good presentations, awesome projects. And Jordan, I forgot Jordan. Yeah, sorry, Jordan. All right, so we've got a few minutes. It's getting late, I know, but we've got a few minutes for discussion, questions, if anybody has anything from the prior discussions.
This is for Ryan. Did you assess the impact of those dropsons using the sensitivities and all that stuff?
So we've been mostly focused on the methodology development. That's somewhat what Sarah's aiming at right now. What I will say is, again, going back to the talk that I gave on Tuesday, most of the sensitive region in most of these storms is right in the circumnavigation windows. So it's hard to say what the sensitive region is giving you. Sometimes it's hard to say what the sensitive region is giving you just flying over a standard pattern. But I'll be willing to collaborate with somebody on, especially on the hazard forecast metrics.
Bill. This is Bill Ramstrom from HRD. Another question for Ryan was, it seemed to me that you were looking at the influence of the wind observations from the dropsons. I'm wondering if, particularly for intensity, if an RH or some humidity measure, if you're also looking at doing that. That seemed like that could be an interesting and important factor as well.
No, absolutely. So in the intensity metrics, the fields are low-level vorticity, steering wind vorticity, and the 500 to 850 hectopascal water vapor. So for each of those metrics, we developed a specific set of fields to compute sensitivity to, based on running it on several cases, but also, you know, some interaction with Wallace, Alan, and others about what would be the fields that would make the most sense for that metric.
All right, looks, did somebody over there have a question? No. Looks like there was some discussion in the chat. Jordan, I don't know if you've been watching to see if there's anything we should bring up here.
Yeah, James Franklin had a question. James, if you'd like to speak to that, or I can read it for you.
Yeah, sure. It was just a question about whether considerations external to the recon data itself might help resolve inconsistencies between, say, the SFMR and the flight level. And it looks like Jonathan answered that yes, he can do that, but he can elaborate.
Yeah, I don't know if I should speak for CSU. I don't know if they're online here, but the neural network is quite flexible. The key would be to have a database where you have, you know, several years of this type of data to train it on. So we'd want to make sure that we do this in the right way. But the existing model had a number of parameters that were I would say, novel or different than you would just expect from the raw data, right? So you can train on factoring in the storm intensity, et cetera. But I think that that convective vigor that you brought up is probably one of the key ones when it comes to intense storms. So we'll definitely try to take a look at this. Thanks.
Yeah, and where you are in the eye wall cycle, I think, can be very informative as well about, you know, how the winds get brought down after an eye wall replacement, for example, is different than beforehand.
And I guess I should also mention one of the other tricky aspects is the degree of eye wall slope and whether there is in fact an overshoot. That plays a little bit of havoc with trying to, you know, co-locate surface and flight level winds. But I think that's a really important thing to treat. And I believe that they are treating that in some way already, but I'm pretty sure we could probably take a deeper look at that.
I just wanted to follow up on this exchange between James and John. I think it's really interesting. And my impression, and I don't follow every cycle of every storm, but my impression is that things early in the storm history of hurricanes, when you know, for example, if you're RIing and you have a small eye wall like Lee, like early on when it was becoming Category 5, it feels to me like something is fundamentally different in that relationship early on in these major hurricanes than later on. And you know, it's probably related to eye wall slope. There's probably something going on there, but you know, I doubt there's a one size fits all for this. I think there's some kind of evolution that we need to think about. No, probably RMW, right? Like this might be like something might be fundamentally different in small RMW storms than larger RMW storms. I've talked about this with Heather. She has not looked at, for example, this in her SON work, the stratification by RMW, and I suggested that she should, and it might be something for you guys to look at too.
Yeah, thanks. I think angular momentum, the shape of the profile in the eye wall, those are all really key things. And yeah,
inertial stability, Jonathan.
Yes. And I agree that young storms that have undergone that primary intensification phase, I think they are a different beast than the later storms later in their life cycle. So life cycle is really important.
All right. Not seeing any other questions. Thanks again to all the presenters. Great session. And I'll turn it over to Aaron for any last comments.
Thanks, Wallace. And thank you, Jordan, and to the presenters as well, and for everybody for trudging through these long days. Really appreciate it. My apologies for the technical and Aaron difficulties that you've had today. Let's see. So if you can force yourselves to wake up and live through half a day here tomorrow, we will be back at approximately 8:35 a.m. We will have a session tomorrow predominantly on developer support and transitions from DTC to Epic for support. And we will also have a talk that I believe Wallace is giving on behalf of Pablo for next generation WSP. And we will also have a talk from Mike Eck on physics across scales, and then a presentation on R&D HPC and kind of what the next few years are going to look like from Radhika Subramanian, and some Q&A on that. And then we'll close out with a session that starts out with Frank Edviglio, the Chief Technology Officer for NOAA, talking about his vision for HPC for the future, as well as user needs, and a discussion on that. And then ending, as usual, with our strategic goal planning discussion led by Frank Marks and Gopal. All right, have a good night, and see you tomorrow morning.
Thanks, Aaron.